we're going to look at the volume of a sphere using the volume of solids method. The sphere is going to have radius r, so that's a fixed number. So we only know that value, so what we're really looking for here is a formula. There's my sphere, so I'm going to just give it some depth here by drawing that in the middle. I have radius r, so I can go ahead and draw any line going out to the edge, out to the sphere, and that length is r. If I go ahead and drop some, let me draw it one more time. If I draw it again, but this time I'm going to run the origin of the axes through my center. That's supposed to be the center. My radius is r, so this goes out to r, this goes out to r. I'm on a directed grid, so those go down to negative r and negative r. So as I put this guy together again, let me go ahead and grab that cross section in the middle. I have, there's my cross section in the middle. I have a fixed cross section here, but as I move that cross section up and down along the y-axis, you could also choose to do this along the x-axis, I notice that my radius changes. So I have this variable radius, and I'm going to call that variable radius lowercase r. I have decided by the way I've drawn these that I'm going to be stacking in the y direction. That gives me my template. So the volume is equal to, I'm going to use y's, y1 to y2. Let's see, I need the area of my cross section, and in the y direction, so dy. This is the area of a circle. So let's go ahead and put that in here. That's going to be pi. R is only when I'm on the axes there, so this is going to be pi lowercase r squared dy. I want to stack them all the way through the sphere. So along the y-axis, that takes me from negative capital R up to capital R. Those are fixed values, so we're okay to leave those there. The only problem I have with this is that lowercase r. I need to get this in terms of y. It's supposed to say a of y. So I need to get that in terms of y. Well, I notice one thing here. As I'm looking at those radii, I notice that my radii always line up to an x value. So no matter what my radius is, whether I'm on the very top here, I'm always lining up to an x value. So I can start by replacing that in terms of x. So negative r, positive r, pi, I can replace that with x squared dy. Still a problem, but as I take a look, I can find a really nice relationship between x and y. I'm just going to grab my circle here. My circle has radius r. So if I choose an x and a y, I can do the same over here. I can say that x squared with the Pythagorean theorem plus y squared is equal to, and that's that fixed radius that I'm going out to, capital R squared. So I'm going to use that relationship, x squared, and it's a relationship on the xy plane. So x squared plus y squared equals capital R squared. I want to replace r, so I end up with x squared equals r squared minus y squared. R squared is fixed, so I'm okay to leave that, and y then is my only variable. Okay, so now going back to my template from here, my volume is negative r to r pi x squared, and I do have x squared. I didn't take a square root yet. Good. So r squared minus y squared dy. I have some really nice symmetry, and that symmetry starts at 0. So I am going to say that the area up above from 0 to r is equal to twice the area from negative r to r. Just a nice way to clean things up just a little bit. So this is equal to 2 times the area from 0 to r. I really like 0 for a limit of integration. I can pull the pi out, so let's go ahead and pull the pi out. And then I'm left with just the integral to do. So r squared minus y squared, remember r squared is fixed, dy. Nice simple integral to work. 2 pi r squared is fixed. We're differentiating with respect to y, so I get an r squared y minus, this goes to y cubed with a 1/3 out in front, and I'm evaluating that from 0 to r. So I get the 2 pi, just crunching through the math here, capital R squared times r minus 1/3 capital R squared minus fundamental theorem of calculus. When I plug 0 in for y, I get 0 minus 0, so I don't need that second term. Almost there. I have a 2 pi r cubed minus r squared divided by 3. And that's the volume of that sphere. Oh, you know what? Yeah, I'll leave it there. That's the volume of that sphere. And I think I did make one little error, though. This is not squared, it's cubed. So r cubed minus r cubed. I'm glad I caught that. So I can go ahead and combine these. So I've got it, but let's just clean it up a little bit. 2 pi. If I call this r cubed 3 over 3, and I'm going to subtract 1 over 3, I get 2 over 3 r cubed. And now it looks familiar to us, so I get 4 pi thirds r cubed. And that's the simplified version of that volume.